This lesson deals with supplemental problem 8.6. You can find this problem in the ECE202 ebook in the Chapter 8 Supplemental Problems on page 5. Given this circuit with a controlled source, can you solve for the current I of t in steady state? Just like resistors, controlled sources also map from the time domain to the frequency domain. So let's use our three-step algorithm. We'll take our circuit in the time domain, convert it in step 1 to the frequency domain, do the frequency domain analysis in step 2, and then convert back into the time domain. Capacitor has an impedance minus j over omega c, and here I've got a 5,000 picofarad capacitor, so minus j divided by 40k and 5,000 picofarads. That's minus j 5,000. And the units on that would be ohms. The inductor is j omega L, so it's going to be j times omega, which is 40k, times 0.5 henries, and I get a j 20k. And again, the units are ohms. My voltage source becomes a voltage source in the frequency domain with a magnitude of 10 and an angle of 0. Frequency is 40,000 radians per second. Resistors just map directly. The impedance of the capacitor is minus j 5k ohms. The impedance of the inductor is j 20k. Now the voltage V1 here becomes a phasor voltage V1, and we're going to multiply that by 5. A lot of ways you could do the analysis, but to solve for this current, I would need to know what this voltage is. And so I can find that over here using a voltage divider. So let's do that. So our voltage divider from the time domain maps into the frequency domain. If I want to find the voltage across this capacitor, I take that impedance over the sum of the two, and then multiply that by the voltage. So I have the same current in two elements. The voltage divides with the voltage divider rule. Let's do division here. Let's put things into polar form. So I have 10 at angle 0, and this becomes just 5,000 at angle minus 90. This is what to put into our calculator. So real part, imaginary part, which is minus 5,000. Magnitude is bigger than 5,000. The angle is going to be in the fourth quadrant, but actually be 45 degrees, negative, because these are the same length. So I'll take the ratio here of 10 times 5k divided by 7.07k, and I wind up getting 7.07. The angles of the numerator add, minus the angle of the denominator, so I get minus 90 plus 45, or minus 45. All right, the current flowing in here would be 5 times this voltage, so 5 times that, divided by the total impedance. Put everything into polar form, so its denominator be a little bit bigger than 20k. We're going to be in the first quadrant, but more than 45 degrees because this is longer than this. So this seems reasonable. Of course, we have this already in polar form. 5 times 7.07 divided by 25k, that turns out to be 1.414 milliamps. And the angle of the numerator, 0 minus 45 minus the angle of the denominator, which is 53.15, gives me a total of minus 98.13. And then lastly, our third step is to map from the frequency domain result to the time domain result by just putting the cosine of omega t between the magnitude and the angle. So my current then is 1.414 milli times the cosine of 40 kt minus 98.13 degrees amps. And this is supplemental problem 8.6.